So Mendeleev was considered a kook for doing this, and he finally said, fine. Where silicon sits now, it sits just below germanium. Well, what is it? I think I've got those mixed up. Where germanium sits below silicon right now. He created, he had no box there. He left empty spots saying we hadn't found those elements yet. And again, scientists thought he was a kook for that. And he ended up creating an element called ecosilicon. It was a fictional element, but he based it on the properties that he saw in that column. He based it on patterns that he saw in atomic mass and things like that. And so he predicted all these properties of this element before it was ever found. And when it was discovered by another scientist, and he and the other scientists actually argued over what the properties should be and what the properties he said should be and the properties that the scientists that discovered it said were there. And ultimately, what ended up happening is when science got to really looking at it, Mendeleev was more correct with his properties without having ever seen the element, which is now germanium, than the guy that actually discovered it. So from that point on, we kind of took on looking at the periodic table as having some more meaning. And over time, we've now found that it's not that the periodic table and the patterns in the periodic table are not related to the atomic mass as much as they are the atomic number. So that gives you a little bit of a history behind the periodic table. Today's lessons are going to be, we're going to understand atomic structure. So we're going to learn the basics, the subatomic particles, things like that. We're going to talk about element symbols and recognize the use of element symbols from the periodic table. Again, we're going to explore subatomic particles, protons, neutrons, and electrons, and we're going to see how those relate to the periodic table, and we're going to be able to calculate mass based on the periodic table, which will allow us to be able to predict the number of protons, number of neutrons, and things like that in elements. All right, so let's get started. Let's start first with kind of talking a little bit about the subatomic particles that make up an atom. First of all, we have the nucleus. And the nucleus contains, as it says here, 99.9% of the atomic atom's mass, because protons and neutrons compared to electrons are huge. They're, as far as the mass goes, they are incredibly, incredibly dense. It would be like, to compare a proton or a neutron to an electron would be like putting an elephant on a scale and throwing a feather on the scale and looking at the difference in mass, because electrons are incredibly tiny, although electrons tend to fill up most of the space of the atom because they form clouds. So the nucleus has all the density of the atom, while, as it says here, it is 1/100,000th the size of the atom. So it is tiny, tiny, tiny as far as an atom is concerned, but it has all the mass, basically all the mass of the atom. And that is because protons and neutrons are very large in size. Protons are positively charged particles, and neutrons are neutrally charged particles. So they have no charge. So I really shouldn't say that they're charged, but they have no charge. And because of the neutrons, they help buffer the protons and allow the nucleus to stay together using what is known as strong nuclear force. And that's one of nature's fundamental forces that allows the nucleus to be held together. If it weren't for the neutrons and the strong nuclear force, the protons being positively charged would repel each other and expand away from each other. But the neutrons act as a buffer in the so that the nuclear force can hold the protons together. Then we have the electrons. The electrons are much smaller in size, but they move around and take up most of the space in an atom. They take up over 99.9% of the atom's physical volume, but they're not very heavy in size. And that is because they are constantly in motion, moving around, trying to stay close to the nucleus because they're attracted to the positive charge of the protons, but they try to stay away from each other because they're all negatively charged, and they try to stay away from each other. So they try to stay close to the protons and stay away from each other. It's kind of like if you were to see starlets at one of those big Grammys or shows like that, if they were all wearing the same dress, they all want to be seen on TV, but they don't want to be seen with someone else wearing the same dress. That's kind of a way to think about it. They want to be close to the camera, the nucleus, but far enough away from each other that they don't get seen together. So that's basically how an atom is built up. So elements and their unique symbols. So on the periodic table, when we look at the periodic table, we usually see, sometimes you'll see the name written small in the box. Most of the time you will just see letters, and all the elements have their own unique symbol, either 1, 2, or possibly 3 letters, and most of the 3-lettered elements are man-made and they haven't been named yet. When you look at the periodic table, you will see things like unium. Well, is 1, 1, 1, unium, 1, 1, 1, or things of that nature. Quadnium, 1, 1, 4. Those have been man-made. They're very unstable. They are so large an atom that they typically have half-lives, which means the atoms disintegrate. If you have 100 atoms, half of them will disintegrate in a certain period of time. The half-lives of man-made elements are in the matters of seconds. So if you were to have a man-made element, smash them together to create an element like unium, and you have 100 atoms of it, after about 5 seconds, 50 of them will be gone. Another 5 seconds, so you're at 10 seconds now, you're down to 25. At 15 seconds, you're down to 12. At 20 seconds, you're down to 6. 25, you're down to 3. At 30 seconds, they're basically all gone. So there's that. But when we deal with the symbols, we are dealing with, like, for example, we have hydrogen here, which has the letter H. Makes pretty good sense. Hydrogen, H. Well, we also have helium, so we can't have helium be H as well, so we call it He. And notice only the first letter of the element symbol is capitalized. That's the way we can recognize when we get to a new element. For example, when we talk about table salt, which is NaCl, the N is capital, the A is not, the Cl is capital, the L is not. Well, NaCl is sodium, Na, and chlorine, Cl. Now, you might ask yourself, why is sodium have a chemical symbol of Na? And that is because it is named, or the symbol was put in place based on its Latin name, which is natrium. The same thing with iron. It's Fe, and it is known as ferrium. Sometimes you'll hear it as ferrous, and sometimes you'll hear it as ferric. And that has to do a little bit with what charge it happens to be taken on. And we're not going to go that deep into this because we're not in chemistry. But we're in the beginnings of chemistry. That's what physical science is all about, is to try to give you a little bit of a glance at what the beginnings of chemistry look like and the beginnings of physics look like. So our elements are the unique symbols. So if I were to ask you what AU represents, the symbol AU, most of you are probably going to have to go to a periodic table to figure that out. Because it's not one of the ones that's obvious, because there are some A elements, but AU is not representing an aluminum. It's actually representing gold. Gold is AU. Aluminum is AL. And again, gold was named after its Latin name. So we have our chemical letters or symbols, which we're going to have to add to that. But the first thing we need to make sure we understand subatomic particles, and remember that protons are positively charged and found in the nucleus. Neutrons are neutrally charged and found in the nucleus, and electrons are negatively charged and are found in clouds moving around the nucleus. They're not trapped and held tight into the nucleus. They take up a lot of, I say they take up a lot of space. They really don't take up a lot of space, but they're kind of like a gas. They move and fill that space, even though there really is an awful lot of open space in the atom. We seem like very dense human beings. We can't put our hands through boards, and well, we can break them, but we can't put them through boards and things like that, like ghosts, even though most of that is just empty space. All right, so now we get to some other things that are usually put on an atomic symbol, and that is the atomic number and the atomic mass. Okay, so first off, the atomic number, and the atomic number is very important because the atomic number is what tells us what element we're dealing with. So it defines the element's identity. For example, if we have an atom that has 6 protons, it's carbon. If it were to gain a proton, it would become nitrogen. If it were to lose a proton, it would become boron. Those are things that we have to recognize. Now, atomic mass, on the other hand, we kind of, and there's a reason why the atomic mass is just the total mass of the protons plus the neutrons. So we add the protons and the neutrons together, and that will give us the atomic mass. The atomic number tells us what kind of element we're dealing with. The atomic mass tells us basically the total mass of the element. We kind of ignore the electrons because, again, as I said, they are so small that they become almost unmeasurable compared to the proton and the neutron. The other reason we ignore electrons is because in chemical reactions, electrons can move from one atom to another atom. So, for example, when I was talking about the sodium chloride table salt before, sodium actually loses an electron to the chlorine, and it becomes positively charged because it now has more protons than it does electrons. It goes from 23 protons and 23 electrons to 23 protons and 22 electrons. So it has one more positive charge than negative. Chlorine, on the other hand, which has an atomic number of 35, it has 35 protons. It has to have 35 protons or it won't be chlorine. But when it gains that extra electron, electrons are negatively charged now, it has 36 electrons and 35 protons. So what kind of charge do you think it has? If it has 36 negatives and 35 positives, it ends up with a -1 charge. And because of those opposite charges attracting each other, that's what allows sodium chloride to stick together. So when we look at our chemical symbol, in this case, we have magnesium over here. Magnesium is Mg, and notice that the atomic number is 12 and the mass number is 24. How do I know that for sure? Well, the easiest way to tell is just to remember this. Remember, atomic mass is protons plus neutrons. Atomic number is just protons. So we always should have a mass number equal to or greater than our atomic number, because this is protons. If we add any neutrons to it, it's going to get bigger. If we don't add any protons to it, it's still going to remain equal. So our atomic number will always be smaller than our atomic mass. I hope that makes sense to everybody. Okay. Calculating neutrons. Okay, when we calculate neutrons, remember I said that the element is determined by the atomic number. And if we look at the atomic mass, so for example, oxygen has an atomic number of 8. And right? Yeah, 8. So if it has 8, then it has to, if it has 8 protons, it has to be oxygen. So by looking at the looking at the number of protons, we know the atomic mass, we know what the element is. Now, how do we find the number of neutrons? Well, if we look at an element and let's say, for example, let's use carbon as like they use down here. Carbon has what are known as 2 isotopes. Carbon, well, it has more than that, but for the most part, it's limited to 2 isotopes. 99.9% of carbon is carbon-6, which means it has 6 neutrons. How do we know that? Well, it has an atomic mass of 12, and for it to be carbon, it has to have 6 protons. 12 minus 6 is 6. So it has 6 neutrons. So carbon 12, protons plus neutrons, has 6 neutrons. Carbon 14, on the other hand, which is used for radioactive dating and things like that, that's how we can determine how old certain things are, because living organisms produce a minute amount of carbon 14 as they are living. Once they die, that carbon 14 radioactively decays down to carbon 12 over time. So those few atoms over time, and it's a couple hundred years, will break down, and we know how much carbon 14 should be there. And if it's not, and if it's less than that, we can do a calculation and figure out how many years it's been since that material was basically alive. So what is carbon 14? Well, carbon 14 is the atomic mass. So the number of protons plus the number of neutrons is 14. But for it to be carbon, how many protons does it have to be carbon? Anybody want to throw that into the chat or say it out loud? I've said it about a half dozen times. Carbon has how many protons? 6, right? So if it has an atomic mass of 14, how many neutrons is it going to have? 8. Thank you, those of you that put that in there. So yes, 8, because 14 minus 6 is 8. And that's, so carbon 14 and carbon 12 are going to act chemically exactly the same. The only difference is carbon 14 is a little heavier than carbon 12. It has a few more neutrons, and that's it. All right. So carbon 14 and carbon 12 are what we refer to as isotopes. And all isotopes are atoms of the exact same element that have slightly different numbers of neutrons. That's the only difference. There's a few extra or a few less neutrons in isotopes. So when we talk about isotopes, we're actually talking about atoms of the same element that just have different numbers of neutrons. And notice here, again, we have carbon 12 and carbon 14. And we've already determined the difference is 8 neutrons versus 6 neutrons. And if you look at the periodic table, you generally will see that elements, if we're just, the atomic mass is supposed to be the number of protons plus the number of neutrons. But if you look at chlorine on the periodic table, it has an atomic mass of 35.45. And the reason for that is because there's chlorine 35 and there's chlorine 36, and they're almost there in equal amounts. So, and when you have almost equal amounts of 35 and 36, the average is going to be pretty close to 35.5. Carbon 12 and carbon 14, carbon, if you look at the periodic table, has an atomic mass of about 12.01, which basically means 99 out of 100 carbon atoms are carbon 12, and one, well, 199 out of 200 are carbon 12, and one is carbon 14. And that's how we get the 0.01 mass. So there's that. All right. So again, naming elements is based on either historical names or scientist honors. The scientists that find them generally get to name the elements. So that's why you see things like seaborgium or californium, berkelium, and there's an awful lot of those elements. There are also scientific names, elements that are named for scientists. Most of the funny names like that come from, or what I consider funny, come from elements that were man-made. So californium, berkelium, those are all named because of where they were made. One of the biggest atom smashers in the world is at the University of California, Berkeley. And so they've had elements named after them. There's Einsteinium, fermium, things like that. Those are named after scientists as well. There are some that are named after where they were found. All right. Is there going to be a new element in our lifetime? You can bet on it. You can almost bet on it. They're out there constantly trying to create new elements. Now, will it ever be really usable? No, because they're so big. The elements that are being man-made now are so big that they just don't hold together. They're not stable and they break down rapidly. So we really don't find any use for them. In my lifetime, I'm 57 years old, and there's been approximately 35 new elements. We say discovered, but we really haven't discovered any new elements. They've all been man-made in my lifetime, the new elements that exist, but they don't really exist for very long. They're not natural because they just can't, the nuclear force can't hold them together long enough to make them stable. All right. Anyone else have any other questions? All right. Well, if not, thank you for coming today, and I hope to see you all again next week. Have a wonderful rest of your day.